So we had our network, which a part of this drawing labeled C shows up as actually a network, and at each of the levels, we imagine that this particular channel is just a pipe with the length L sub k and the radius R sub k, through which a liquid is flowing, and we are using the formula which we had derived previously for the current flow, a rate of flow through this pipe, which is proportional to the cross-section of the channel and the average velocity through the channel, which I denoted as a U with sub k. Our assumption is that the amount of fluid which is passed through the system is conserved, that there is no loss of the blood or of any other liquid in the system, and that of course allows me to I have to get rid of this. Derive a very simple formula, namely that first, that at each level of this network, the total number of branches is equal to the product of all the number of branches, and how each branch splits in the previous layer, and we also assume that the flow is conserved, as I said, and that means that the current which is flowing into the zero level channel, that is, which is to the left of my drawing, must be preserved, and that allows me to write the following formula. If that formula is written, then I am making the basic assumption, so to say, that the metabolic rate for the system is proportional to the rate of flow in the level equals 0. If that assumption is made, we have to proceed further and make a next assumption that the capillaries are size invariant. If the capillaries are size invariant, that means that the radius of the capillary, which is the end level of our fractal, a length of the tube L sub c, the average velocity flow, and the pressure drop is independent of the total body of that living structure. And that, of course, means that if we make a basic and logically quite feasible assumption that the metabolic rate B must be proportional to the mass of the living structure with some exponent A, which we don't know what it is, then the Q0, the flow through of a blood or the liquid through the level 0 channel, must be proportional also to the mass of the body with the same exponent. And that means that the total number of the tubes, elements of our network at the capillary level is also proportional to the mass with the exponent A. And we will now use another basic assumption that the energy in our system is conserved. If energy is conserved, to use this, we have to make a small change in the notation. We introduce the dimensionless numbers, which tell us how the radius of the tube changes with the level in the network. and that is called beta K, and this is a ratio of a radius of a tube in the level K plus 1 to the level at the rate K, and the gamma K, which is the ratio, is dimensions number telling us how the length of the tube changes, and the nu, which is the same dimensions number telling us how branching of the tube at the level K is related to that at the level K plus 1. And the conservation of energy implies, and that is a piece of the calculation which is a bit involved, and I decided to tell you that you should take it for granted, that energy conservation actually is equivalent to saying that these dimensionless numbers are constant, are independent of the level of the network. Out of that, it follows that the branching of a tube at each level is a constant, and there is a certain constant in our system which is called a little n. All right, so we now can use this conclusion from these three assumptions that we just have made, and the fact that our network is self-similar, and that implies that the total number of capillary vessels is simply that constant little n to the power total number of the tubes in the system, and therefore I can write that the number of capillaries is equal to the mass to the power a. But since the number of capillary is a number and the mass has a certain dimensions, we cannot write the equation which compares the variables which have different dimensions. That's mathematically impossible. Therefore, I have to make an assumption which is completely irrelevant for the further analysis, that we have some scale of the mass in our systems, which I have denoted as a m sub 0. And then if I divided the mass of the structure by the m0, this is dimensionless number, and therefore the formula that the number of capillaries, total number of capillaries, is just this m divided by m0 to the power a is mathematically correct. All right, therefore the n to the power capital N is equal to this ratio to the power a, and this is a simple use of a logarithms that allows me to derive the allometric exponent a, and it turns out to be capital N times logarithm of little n divided by the logarithm of the masses. So now I have to calculate somehow the right-hand side of that equation in order to get the value of the number a. As you see, we are not using any other assumptions than a simple laws of physics, that the conservation laws, that the liquid is, the total volume of the liquid is conserved, that the energy is conserved, and the assumption that the self-similarity of the fractal structure of this network. All right. So that is an interesting conclusion which follows from this equation for the allometric exponent. If you take a mice and a whale, the ratio of the mass of those two creatures is 10 to the minus 7. So that formula immediately tells us that there is about a 70% more branching between the main aorta, this level 0 in our network, and the capillary in between the mice and the whale. So the fact that there is a logarithm in this expression immediately tells us that we are close to the final result, namely that our result is independent basically of the size of the structure. Perhaps it is interesting that the very similar relations holds also in economy. And many years ago, a very important for developing of a statistical mechanics and modern application of mathematics, American physicist Elliot Montroll had contributed a paper to his own Festschrift, a book written for him on the occasion of his 60th birthday. And that paper was remarkable, namely he analyzed, in our course language, we will call it allometric exponent for the growth of the prices in the Sears and Roebuck catalog. Before internet came into existence, there was an institution in the United States called Sears and Roebuck. This was a department store which since years was publishing a catalog which contained all the items which were offered in the store with the prices, and people were able to purchase those items via mail. So that was something like today internet shopping via mail, and perhaps this is why this internet shopping had grown up so dramatically fast in the United States. And what Elliot Montroll has done, he took a collection of Sears and Roebuck catalogs since the first catalog to the last catalog he got before writing the paper, and he calculated. He first of all he written down all the prices, were all the items mentioned in this catalog, and they are items which were costing few pennies, and there were items which cost thousands and thousands of dollars. So in order to compare different sizes of the prices, so to say, the different, which is the value of the item, he calculated the logarithms of those prices and then plotted a histogram for those prices as a function of the issues of the catalogs. And it turns out that this histograms of the prices in all the Sears and Roebuck catalog turned out to be essentially allometrically self-similar, and that their width of the histogram, which is something like a standard deviation of the histogram, were constant in time, including a time of a great economic disaster in the 20s. So that is basically this formula we derive now, which already says that the animals on the sizes as different as a mice and a whale are the same. So we continue our analysis, and let's calculate the total volume of a fluid in our network. The total fluid in our network, which I denoted as a V with index B, is a sum of the number of the tubes, branches at the level K, times the volume at the level K's, and the sum over all possible levels. And since the volume of the channel at the level K is very simple, is a cross section of the tube times its length times the n to the power k, so we can calculate that sum. That is a very, very simple calculation from high school, and that is the final results. It's a complicated expression, so I can simplify it by making the simplification based on the assumption that the number n is huge and that the product n gamma beta square is small. If I do this assumption, then remember what is the meaning. In order to make this assumption that n times gamma times beta square is less than 1, a meaningless assumption, we have to recall a definition of gamma and beta. Beta is a ratio of radiuses, gamma is a ratio of length, and n is the branching number, how many branches a given tube branches. And that assumption means that these channels are, so to say, pretty narrow and not particularly long, and that they do not split into too many of the branches. And with this particular assumption, this expression can be simplified enormously, and it says that the total volume of a liquid in the network is a volume of a capillary times a very simple formula. So since capillaries are, as we already made this assumption, size invariant, that implies that the ratio, that the product of a gamma times beta square to the power minus n must be proportional to the mass of the animal, of the living structure. So if I substitute that in this expression, then I easily can calculate the exponent a. And now I have to guess what are the values of beta and gamma. And we remember that the a is then logarithm of n divided by log of gamma and beta squared. So if I figure out how to make an educated guess what are the values of gamma and beta square, then out of that formula I will have my formula for A. So, all right. So I am making a further assumption that all cells in the body are serviced by the capillaries. That is the very sensible assumption. And with that, I can approximate the volume for the of the network at each level by a sphere, which is having a size. I'm approximating a cylinder of a tube by by a sphere with the radius equal to half of the with the radius, which is Lk divided by half, and there is a n sub k pipes in at the level k. So this is an approximation for the volume. And we still remember that the Rk is less than Lk. So this is a sensible approximation for the volume Vk. And if I do this, then volume preserving networks, I have the following expression, which relate me these volumes at each level of my network. And out of that, it immediately follow. I can immediately derive the expression for gamma. Remember, gamma is a ratio of the L's, and it turns out that the gamma to the power cube is equal to 1 over n. So with this assumption, I made my educated guess what is the value of the gamma in the expression for A. So gamma is proportional to the n to the power minus 1/3. So now I have to calculate the beta, and I am making the assumption for beta assuming that the cross-section of a daughter branch is equal to that of the parent. If I make that assumption, then the cross-section for a pipe at the level K is equal to the cross-section of the tube at the level K plus 1 times a number of the N, which is a number of branches into which branch at the level K splits. So out of that formula, I derived that the beta is proportional to is inversely proportional to the square root of the number N. So now I'm home, namely I have the formula for the allometric exponent, and both beta and gamma are proportional to the N. So if I substitute here, that I get that that what sits in the denominator is proportional to it is a logarithm of N to the power 4/3, and that means that logarithm of N cancels and A is equal to 3/4. And that was the reason why the allometric exponent we had at the beginning of our lecture is for humans and for animals, for the bird eggs, and for many, many other important relations between sizes in the biology of a living organism is equal to the 3/3. And in addition to the geometry of the network, which is a physiological property of a human body or animal body and of many plants, and the only real assumption which was made, it was that the fluid is conserved, the energy is conserved, and that the flow through the channel at the level K is a Poisson flow, which we discussed. So that should convince you that also in more complicated cases, a hydrodynamic analysis allows us to understand many important properties of biological systems. All right, so we are now for a while through with the fluid dynamics, and this is a fifth part of my lectures, which is devoted to the science of heat. I use the title for this chapter, The Kind of Motion We Call Heat. This is the title of a book about the history of that science written by American physicist Stephen Brush. And that's a very good book, very, very nice historical book, which has a very interesting, there is an interesting story with this book. When Stephen Brush was writing the book, he had discovered a fact which was related to University of Warsaw, and he wrote me a letter asking whether I can help him with some information about it. And it turns out that that was very difficult to get. It refers to the question was related to the book written by Professor Stankiewicz, who was a professor at the University of Warsaw, and this was a Russian Tsar university at the turn of the 19th and 20th century. And all the documents related to that part of the history of the university was sent to some storage place out of Warsaw, but eventually the information about this gentleman was found. All right, so we are now going to discuss a science of heat and possible application of it to the biology. And when we are learning something like mechanics or fluid dynamics, that's what we were talking until now, then we were talking about the something which was objectively available to the human consciousness. We were completely aware of what we are doing when we were measuring the length of the path covered by the javelin thrown by a hunter, or we more or less were aware of what is the role of the mass of an object and so forth. But there are several other human senses which we use in the everyday life and which are very important for us, which are hardly susceptible to some measurements. For example, we have taste. We can tell whether the hamburger from that particular food truck is more tasty than the hamburger from the other food truck or from a stand on the railroad station. But we do not have a scale of taste. We do not have a measure of a taste. We cannot tell that the hamburger from Burger King is having a taste number 2, and the hamburger from McDonald's or from the Vendy is number 4, or the other way around. We do not measure it, although we use the concept of the taste, because it is related to our senses. And a similar, for example, is with the smell. We are able to qualify cells because of our senses, but we hardly can tell that the Chanel 5, which is on that particular drawing, is having a number. Well, the 5 does not refer to any numbering of the smells, but the Chanel 5 has a smell number 5, and the other company perfume have the smell number 3. So again, we don't have it. And some of you might have seen a movie, Perfume, which was a great movie a few years ago, where it's a book about the drama caused by an individual who is hunting for developing the ultimate smell, whatever that means and what is. So if you will have a chance, try to see that movie. And we also have other senses, and the one of this, which in contrast to the taste or smell, led humans to creating a science, is a feeling of warmth. All the animals also have a sense which tells us, allow us to grade various objects according to the feeling, what we call a warmth. And that particular phenomenon can be measured and can be made not only qualitative, but also a quantitative observation. So we start with a short history of the feeling of warmth had been first formulated by bringing in a notion of a temperature. That seems to be obvious for everybody now, what is the temperature, but actually the temperature had a long and interesting history. So imagine you have an object which is depicted as this brownish structure, and we had another object which is a green cube. But our sense of warmth allowed people since I don't know when to tell that a feeling of the brownish and green are different. And we develop a notion that the one of them is warmer than the other. And in order to do this, we had to compare this object and that object with something else, for example, our hands. And we, by touching it and comparing a feeling of a brownish and greenish objects, we can tell what is warmer, which one is warmer and which is slightly less warmer. And the people used to call the less warmer object cooler. All right. So that particular property of our senses allow us to introduce a notion what in contemporary science is called the thermal equilibrium, and which in fact is one of the very fundamental laws of nature, which is called the zero law of thermodynamics. Now let's imagine we have two objects, our brownish and green object, and by touching them, we realize that the feeling of warmth of both of them is the same. So we say that they are equally warm. And let's say that they have the same temperature, the same feeling of warmth. And let's imagine that we have identical box, a little box, and another third object, which is a cone, and with the same feeling of warmth, the same hands, we find out that the box and the cone give us the same feeling of warmth. So let's call it that they are having the same temperature. What will happen if we will take now a pyramid and a cone? Well, with the same apparatus, which our hands, or whatever else we will use to film the warmth, we will find out that the prism and the cone are having the same temperature. The feeling of warmth is the same. They feel equally warm. So we have a situation. If the prism is the same feeling of warmth with the box, and the box is having the same feeling of warmth with the cone, then the prism is having the same feeling of warmth with the cone. So we can say that if that feeling of warmth is the same, that the prism and the box are at thermal equilibrium. And the box and the cones are at thermal equilibrium. And the experiment will tell us that the prism and the cone are at the thermal equilibrium. And then we immediately observe that this notion of having the same feeling of warmth, or which I now call being at thermal equilibrium, is the mathematical property, which allows me, between all objects to which I can attach my hands and check the feeling of warmth, I can split all those objects into the classes of being in the thermal equilibrium with itself. And if the system A and B are in the equilibrium, which I denoted by whatever mathematical symbol I would like, but for example, like this. And if the system B is at the thermal equilibrium with the system C, so what follows from that relation, that A is at the thermal equilibrium with C. So we have one of the De Morgan laws of logic fulfilled, and the categorization of object as being at the thermal equilibrium with itself is a good mathematical definition. And that is a law of zero thermodynamics. If the systems are at thermal equilibrium, we can bring them in, and the notion of being at the thermal equilibrium means what is written here. What we should remember is that this was all depending on what kind of experiment we were using to feel the same warmth of the system. And that had allowed us to bring a concept of a thermometer. And again, we have our three objects: a prism, a cube, and a cone. And they are in a thermal equilibrium. And we have found the thermal equilibrium by using our hands or whatever device we had used, which allows us to tell that they are in the thermal equilibrium. And that measuring device, which I denoted as a thermometer, a medical thermometer, is a physical object. And if this object is in a thermal equilibrium with the prism, with the cube, and with the cone, it defines me. There is some reading on that thermometer, that device, and that reading I will call a temperature, and then not as a temperature of with a level 1. All right, and now I imagine that I have other three objects: another box, a ball, a kind of a football, and the cylinder. And I use the same device, the same thermometer, and I find out that all these three objects are in a thermal equilibrium with itself. And the reading of that machine gives me the number T2. So now I can tell that with my temperature, my device T, with this thermometer, I can measure a temperature of all objects with which I can attach my physical apparatus called a thermometer. And that number, T1 and T2, is what we call an empirical temperature. It's empirical because it depends on the device which we use to measure the temperature. And it took a scientist a long time to find out that this empirical temperature is actually related to something which is called absolute temperature, which does not depend on what kind of apparatus we use to measure it. Okay. So now the history. The history of I started with this picture of the human hands giving us the feeling with which we touch an object, and that provides us with the feeling of warmth. So the concept of the warmth was always related to the human body. And over the course of the history, it was always related to the state of health of the humans. People very quickly found out that the people, when they are sick, they have a different, they are warmer than when they are healthy. Although the fact that all the healthy people have basically the same temperature was not known until the roughly 16th century. And people were getting sick, and people were trying to cure themselves from the sickness, and they were preparing all sorts of different mixtures which were they drinking or eating, which were supposed to help them. And they were known that some of those mixtures are applied for local medical doctors, which were local priests or shamans or whoever. And some of those medicines were used to lower the temperature of a human body, and some of them were used to raise the temperature of a human body. And since in the Latin, the word temperatura means a mixing, actually was originally referring to the mixtures of herbs or whatever used to increase the temperature. So that kind of a mixture had a certain temperatura, and the mixture which was lowering somebody's body temperature was having a different temperatura. And that is why the medical people have created the first scale of a temperature. And if one of the first, or probably the first well-known scale of temperature, has been created by Galen in the 2nd century before our time. And he defined a form, 4 temperaturas for warm, and a 4 for cold, and a 1 temperature which was a normal temperature. But the normal temperature was always for a given man. The fact that they are equal for, as I said, for different humans which are basically healthy, that was not truly known. We know that the temperature of a perfectly healthy people is not exactly equal, but nevertheless. And there was no well-described definition of those degrees. They were rather, as I said, related to the particular kind of a medicine applied to the sick individuals. And we had to wait until the 16th century when Johannes Hasselrus had written a book, De Logica Medica, and he codified at 9 degrees of Galen. There were 4 temperatures which were higher, and the highest temperature with the number 4 was for those living on the equator. He thought that the body temperature depends on where on the globe you are living. And the -4 temperature, Hasselrus assigned to people living on the North Pole. And the normal temperature, which we will today call the 0 temperature, was assigned for those living, roughly speaking, on our latitudes. And this all was more or less same. And the first thermometer, a physical device which allowed to measure a temperature and make it independent from the mixtures of herbs or whatever, was a thermometer device at the end of the 16th century by Galileo Galilei. And that was the first thermometer of Galileo, which I have shown here. And that was a pipe, ended up with a sphere. A sphere contained some gas, and the pipe was up to a certain height from the bottom, filled with the wine. So that was the use of the alcohol in medicine, which prevailed through all the history. And when the gas in that sphere was heated, then it expanded and it pushes the wine down the pipe. And very soon after that, a student of Galileo, Torricelli, had invented a barometer to measure the temperature. What is particularly important is that we in the history of science, we learned that the many objects of physical observations and many concepts have been independently and often before they were discovered in Europe, they were discovered in the Far East, in China. For example, a magnet was known in China. Never mind that it has never been used properly in China. The Chinese people were basically using it as a toy. They have not used it to guide, for example, ships on the open ocean or even the army on the dry land. And that is not the same situation with the thermometer. The first thermometer was brought to China in the 17th century, essentially at the end of the 17th century, by one of the Jesuit missionaries. And he brought the thermometer to China. The name of this individual was Ferdinand Verbiest. And that was how the thermometers have been brought to the Far East. All right. But the humans had been already in the 16th century. Scientists were very interested in actually what is this warmth? What is that feeling? Because once they learn how to measure a temperature, and the temperature scale of temperature have been established. As you know, there is a long history, and we don't have time for it, about different scales of temperature, because I mean, what is the zero temperature was differently defined. Fahrenheit, a fellow from astronomer from city of Gdańsk, formerly Danzig, who had left that city very early and spent most of his life in the Netherlands. He used as a liquid in thermometer a mixture of a water and ice. So the temperature zero was the temperature of the salty water freezing, and the story is that he used the water from the Baltic Sea, but that is not true, and that is why the Fahrenheit scale is shifted with respect to the scale of a Celsius, who is a Swedish scientist, and he had the zero temperature on what is the temperature at which the ice and water coexist with each other, and at the normal pressure, and that is a Celsius scale. And there was a Réaumur scale, which is a French scale, and the Celsius is from 0 to 100, and the Fahrenheit is particularly difficult. If you want to convert the Celsius scale into Fahrenheit, you have to subtract or add 32 centigrades and divide by half, basically by half. And the Réaumur scale is from 0 to 80 degrees. I remember when I first time came to United States in the 70s, and I was I was initially unable to adjust to the Fahrenheit degrees. So I wanted to get a thermometer which had two scales, a Celsius scale and a Fahrenheit scale. And that was almost impossible. And finally, in a store with the kitchen gadgets, I asked the salesman there whether he has a thermometer with two scales. He says, sure, I have. And he gave me the box. I bought the box, and at home I find out that it had the Celsius and it has a Fahrenheit and the Roy-Meyer scale. So I finally had to learn the Fahrenheit scale. And anyway, the scientists were very interested in the qualitative and quantitative notion of a temperature. And there's this difference. The colder substances, for example, when we touch the ice, and the warmer, when we put the hand into warm water, we have a different kind of feelings. And at the end of the 16th century, there was a particularly important philosopher living in France, Pierre Gassendi, who in one of his books called Syntagma Philosophicum had written the following. He had been very interested in what is the cold and what is heat. And this is a quotation from that book. Cold produces specific and very familiar effects on our senses. And since cold is antagonistic to heat, the atoms corresponding to it must be a nature opposite of that to the atoms generating the feeling of warmth. Heat characteristically dissociate, while cold characteristically contract. Hence, the atoms corresponding to them must have specific masses and shapes, move in a special manner, and thus generate what we usually call heat. I am showing you this quotation because it contains essentially that sentence that the heat is a motion, the kind of motion we call heat, but also that it tells you that already at the end of the 16th century, a scientist had this peculiar idea that the matter around us is actually granular, that it consists of the objects they couldn't see, but they convinced them, and they even call them atoms, that they are building blocks out of which the matter is being built. And that is the way of thinking which is with us until today. We know that the matter is built of atoms and molecules, and the atoms are built of the nucleus, contains a nucleus and electrons, and the nucleus consists of the protons and neutrons, and they are called hadrons, and these hadrons consist of the particle we call objects, we call quarks and gluons, and we have this is our understanding, and we still are searching for whether there is another layer of the structure, whether these objects are not consisting of something else and something else and something else. So somehow the human mind had been extremely stable in understanding how the structure of a matter has been built up by the evolution after a Big Bang. So the interesting thing is that the Gassendi thought that when something gets cold and it freezes, it must be the phenomenon due to the penetration of a matter by the atoms of cold. And that the atoms of cold must be different than atoms of heat. And the atoms of cold, in a further part of his book, he figured out that since the cold object, the crystallite ice and other crystallite objects are having a sharp edges. That means that these cold atoms must be sharp-edged structures, and the feeling of warmth is nice, so that must be spherical objects. So the heat atoms were spherical, and the cold atoms were sharp-edged objects. And this, of course, is not true. There are no different kinds of atoms, but already Gassendi was telling us that in order to understand the heat, we have to think about the motion of the elements out of which the matter is built. And that is how at the end of in the middle of the 19th century, the understanding of a nature has developed, which is called the kinetic theory of matter. And there are basically three simple principles of the kinetic theory of matter. The principle number one is all matter is composed of small particles. Now we know that these are atoms, molecules, ions, electrons. And point two, those particles are in a constant motion. And point three, these particles are constantly interacting with each other and with the walls of the containers it contains. So there were three basic ingredients of the kinetic theory of a matter, and we will try to use them in discussing the three basic phases in which the matter around us is shown to our senses. And they are called gases, liquids, and solids. And this drawing shows us descriptive way what are the distinction between the solids, liquids, and the gases. And the arrow on the top and the bottom of the drawing shows in which direction the energy is increasing or decreasing if we move from one phase of the same substance to another. So the solids which are the leftmost column, are arrangements of the particles which are in a strong interaction between themselves. They are very close together and are, as it is written here, neatly arranged. They, in fact, form well-defined special structures. We will be talking about the solids, but it perhaps should already mention that the solids are mostly crystalline structures. And although we have hundreds or so atoms and God knows how many different molecules, the crystalline structures, the way how these atoms or molecules are geometrically placed in the 3 dimensions of our space is very limited, and there are only very few of those structures which are available, and they're classified in what is called Syngonia classes. And there is a very beautiful part of mathematics developed in the 19th century, which is called mathematical crystallography. And the first book on mathematical crystallography I know, and historians of science are telling that this is true, is a book written by a mathematician from Krakow, Stanisław Zaremba. And the particles in a solid are moving, but since they are close packed together, and they are arranged in the special structures, they do not move freely, but they just vibrate around the given position. So the solid is a tight arrangement of atoms which is shaky, which is all the time shaking. And that shake we can feel by touching a solid in the form of a warmth, and we can hear if we are hitting a solid and hearing a sound propagating in it, and we can observe in many other ways. Liquids. Liquids are also assembly of particles which interact with each other, but the interaction between them are a moderate strength. The particles are still close together, but they are but allowed to change the position. And they do not sit in one particular place for most of their life. They move around, but that motion is organized in some way because there are so many of them that in order to move, they have to push around, and that motion is therefore essentially different than the motion, than the vibrations in a solid. But since they move, they have to push around the dense environment. If we will take a snapshot of the liquid, and we can now take the snapshot of the liquid either by using the physical observation in terms of the neutron scattering, taking a picture by neutron scattering of X-rays, or by taking a snapshot of how the atoms or molecules move by using a computer simulation for a given particular system, then we can find that we take a snapshot, the motion of the atoms in or particles or molecules in the liquid can, for a very short time, not be very much different than the motion of the atoms in solid. And macroscopically, the liquid does not have a shape. If we split, it will go over all places, right? But it has a definite volume. And when we increase the energy of the particles, we end up in the gases. Gases are the assembly of molecules of particles or atoms with a very weak interaction between themselves. What is meaning very strong and very weak interaction we will learn in a moment, but this is the very important that they are weakly interacting, they move very freely, and only occasionally they are so close to each other that they can feel each other. And since they are close to each other rarely, and also because there are less of them in a given volume, they can move much faster, so they spend much shorter time next to each other, and that interaction resembles a collision. And the predominant interaction between the particles forming a gas is that of the collision. So the very good model for many of different gases is simple a model of a hard balls which move in a space, and like a billiard balls, they collide, scatter, and they move in a different direction. And gases do not have any shape, and also they do not have a definite volume. So, having this in mind, we will start talking about the gases. But before we will be talking about the gases, we have to say a few words about the interparticle interactions. All the particles, and let's initially talk about the atoms. They interact, and the interaction is due to the fact that the atoms consist of the nucleus and electrons around it. Both nucleus and electrons are charged. Electrons we call are negatively charged, and the nucleus is positively charged. The notion positive and negative has been associated with given objects since the time of Benjamin Franklin, and these are just names. We could equally call electrons charged plus and protons, the particles which give the charge to the nucleus, as a negative, but historically we assume that the charge of electrons is negative. The difference is that the negative and positive charges attract each other, and the charges of the same sign, they repel each other. And that is the interaction, the Coulomb interaction, the electromagnetic interaction, electric interaction between the electrons and nucleus is one part of the interaction between atoms. The other part of the interaction is that the particles like electrons in the atom and the protons and neutrons in the atomic nuclei, they are subject to the laws of quantum mechanics. And the quantum mechanics is a different science than classical science. And in addition to the potential interaction and the collisions and things like this, there is an additional part of the possible interaction which comes from the fact that the particles, small particles obeying laws of quantum mechanics, they have an additional property. The additional property which is associated with the statistics. And all the particles are divided into the particles which are fermions and bosons. There are two kinds of quantum statistics to make the things more complicated. And the names comes from the names of distinguished scientists, Indian scientists, Bose for one, and the Italian congenial scientist Enrico Fermi. The electrons are fermions, and the fermions have a very peculiar property, namely that they do not like to be in the same energy state as the other. And there is a particular kind of repulsion between the fermions, which comes out from the quantum mechanics. And that is because the atoms have the electrons. When you bring the electrons, the atoms close to each other, then there is also this repulsion between electrons on the orbits in the atoms, which adds to the interaction due to the charges of those objects. So if you do this all together, then this is the drawing of the potential energy of interaction between the atoms in the nature. There is an attraction, which is drawn here as a green line, and this is basically an attraction between the charges in a system of an opposite sign, and there is a repulsion. A part of it is a Coulomb repulsion, and a part of it is this very special repulsion due to the statistic, quantum mechanical repulsion. So if you add green and red energies, you get the blue kind of energy, and that is the energy of the interaction. When the atoms are close to each other, the potential energy is very high and is repulsive, so they cannot get too close to each other. And when they are a certain distance from each other, then they attract each other, and they may form a bound state, a state that they are close together and they hold together, and this is why the solids are being built. And I'm showing here a real potential for the interaction between the atoms in the noble gas argon. The interaction is having this particular kind of interaction is having a special name. It's called Lennard-Jones Potential. This was a gentleman, Lennard-Jones, and double two names. And this interaction is, as you see, very beautifully, almost identical to what I have written. This repulsive part is the positive part in the expression of a potential, and it depends on a distance from the center of the nuclei as a r to the power minus 12. And then there is attractive part with the minus, which is decreasing with the distance as a power minus 6. This is a Lennard-Jones potential. And the liquids like the argon, helium, xenon, and so forth, they are mostly having this kind of a potential. When we have a system built up from the molecules, then the interactions are much more complicated. The final remark about the potential is that this is interaction between two atoms. And one of the most important property of matter around us is that the dominant interaction in the matter around us is a pairwise. So if I have a container which is filled up with the argon, then I can calculate the total energy of the interaction between those atoms in the container by summing up a different interactions energy between different pairs in that volume. In some situations, it turns out that in addition to the interactions which are only those between two atoms, there are also interactions, specific interaction, which exist between three particles at the same time. The triple interactions, and it turns out that they are also important in the noble gases, particularly in argon, but only when we want to crystallize the argon. And they even have the name, they are potentials which are called Axelrod-Teller forces. But for most of the cases, the interactions are simply pairwise. So we are having a certain notion, and now we can obviously see that if the system is very dense, if we put up the particles very close to each other, then the distance between the particles is comparable with the region of negative energies in the interaction, then the particle will try to stay together. But if the density is very low, and if the particles are far away from each other, then the details of this interaction, so if the lambda is large, then the distance of this interaction is, the nature of that attraction is pretty relevant, and we can describe this as a billiard ball with a certain effective radius, which are moving and only colliding with each other. So let's talk about gases. This is the picture of the gas. We have a container, and we have the particles moving in it, and mostly they move with a constant velocity, and they very rarely approach each other and hit each other and collide. And that is happening when a mean distance between the particle, which is the inverse square cube root of a density. Density is measured in centimeter cube or meter cubes. Then the length, this length is in the meters. And when the density is low enough, so the mean distance is larger than lambda, our approximation that we envisage this is a free particle moving at random and only colliding between each other and with the wall is a pretty good picture. So we will finish with a short calculation. Imagine you have a container, and container has a length L, and the area, it's a box with the area A, and we have a particle with the mass M, and they are moving freely inside of that container. So imagine a particle with a velocity v, which is moving freely. It doesn't hit anything before it hits the wall. And when it hits the wall, it scatters. And I will make an assumption that when it hits the wall, it scatters elastically. Then what does that mean? The elastic scattering is a scattering in which the energy is conserved and the momentum is conserved. Momentum is a product of a mass of a particle times its velocity. So this is, of course, what is not happening very often in physics, but it's a good approximation if I have a light atom, like the argon atom, which is hitting an iron wall of a container. Because the iron is much, the atoms of iron sitting in the wall are much, much, much heavier than the atom of argon, then there is a very little energy loss in that collision, and the argon atom scatters back. So what I will now do, I will calculate what is happening to the second law of Newton in that process. And the second law of Newton tells us that the change of the acceleration of a particle, change of the velocity of the particle in the process of a collision is proportional to the force which is acting on a particle. So the change of a velocity I have denoted as a delta V, and I had assumed that this is the x direction, that the particle moves in the x direction. That is why I had written x there. The mass is the mass of the particle. And I'm saying, what is this change of velocity and what is the force in a period of time, in a time delta t? And elastic wall collision is being assumed. So what is the delta V? The particle comes with the velocity Vx, hits the wall. Now the energy is conserved, so the length of the velocity will be conserved, because energy is conserved and energy is 1/2 mass times velocity square. So the velocity square root of it is a length of the velocity. So the velocity is therefore conserved, but it was moving forward, the wall hits and now move backward. So the velocity changes by twice the value of the velocity. So the change of the velocity, delta Vx, is twice the modulus of the velocity. The velocity going in that direction is positive, going in that direction is negative, but I have used but it is minus the negative value, so that value is simply twice the velocity. So what is the time delta t? If there is no other atom in the box, then the particle comes, it hits the wall, and it goes back all the length and hits the other wall. So the time I am considering is at twice the length of the box, going this way and backwards, divided by the velocity. So now I have delta t, and therefore I can calculate out of my expression on top of the page, I can calculate the force. And the force is mass times velocity square divided by the length of the box. But the box is three-dimensional. So the particle is not always moving in the x direction. It can only move the y direction and the z direction. So the velocity is a vector which has 3 components, and therefore I have to replace the length, the velocity along the x-axis by a mean velocity. And a mean velocity is there should be a square root here, I'm sorry, the screwed meaning, but the mean velocity is a mean velocity of a square of a vector divided by 3. There's a square root of it. But here, fortunately, there is a v square, so therefore the force is proportional to the mean velocity square divided by 3. The factor 3 comes that this is a 3-dimensional world. All right, so now I want to calculate the pressure. We know that the pressure is a force exerted on a wall container, and since the area is A, then the pressure is the force F divided by the area times the number of particles which are in a gas which hits the wall. Okay, so since I have the force F, I know what is the area A, I can put that formula in, and I have calculated the pressure is the mass of a particle's number of atoms times a square value of a vector V divided by the script V, and the script V is a volume of the container. So at that stage, I might completely forgot about my high school derivation, and I have the formula that the pressure is mnv square over 3v, and since the mass times the velocity square divided by 1/2 is a mean kinetic energy, so the pressure in that model of a gas is a 2/3 of a density, and divided by volume is a density times kinetic energy. So the assumption that the gas consists of the particles which move and collide with the wall provide me something which we were discussing at the beginning of a chapter on the liquids under the name of equation of state. We have a relation between a pressure and the kinetic energy. And we remember from that discussion and also from the high school that for ideal gas, the gas of a free atoms which only collide with the walls is having an equation, it's rho times temperature, and there is this coefficient, Boltzmann constant, which allows us to convert temperature into energy. So comparing that phenomenological equation of state for the ideal gas with our derived formula, we obtain a very important 2 equations, that the kinetic energy, mean kinetic energy of a gas is proportional to the temperature. Is proportional to the temperature, and it is equal 3/2 of the energy. Since the kinetic energy is mass over 2 times SV square, we have the beautiful relation between the mean velocity of a particle in a gas and the temperature. And that is what you remember from the high school, that we say that the temperature is a mean energy, kinetic energy of a particle, square root of it. But this is not really true. It's only true for the ideal gas, for the gas of non-interacting particle contained in the volume V. We will see next week how that formula allows us to assign a temperature to any object we want in the experiment. All right, thanks a lot.